Continuing on, well, there is a formula to find the standard deviation from a frequency distribution. Now remember, mean, standard deviation, all of these, we're going to use the calculator to figure that out on its own in the coming chapters. For now, we're doing things the hard way, but once we get how to do it, we're going to use technology for that. This, however, we will learn how to do the hard way. Well, it's kind of the long way. Recall the following table gives the weight of sample of 100 babies born in a local hospital. So when the number n is large, there's the frequency. So they do it in intervals. How many babies were born between 3 and 4.9 pounds? 5 of them. How many babies were born between 5 and 6.9 pounds? 32 of them. So if you add those, you'll get 100. Now, the midpoint, if you remember, take 3 plus 4.9 divided by 2, that's 3.95. Take 5 plus 9 divided by 2, that is 5.95. And if you do it for this, it turns out to be 7. We did that already. We do it for this. That turns out to be 9.95 if you recall. And if we did it for this, it turns out to be 11.95. Now multiply those two. Take 5 times 3.95. Take 32 multiplied, again we did this already, 40 times 7.95. Take 18 times 9.95 and take 5 times 11.95. I'm going to show you how to do both of those. Here you want to multiply by the squares. And we want to add those. So I'm going to show you how to do that on a calculator. I should have been using the calculator a bit more. So if I get my calculator, which is still right there, and if I take 5 times 3.95 plus 32 times 5.95 plus 40 times 7.95 plus 8 times, 18, not 8. 18. Oops, I messed up big time. Plus 18 times 9.95 plus 5 times 11.95. I should be getting a total of 766.75. Unless I made a mistake, let me just make sure. 5 times 3.9, 32 times 5.95, 40 times 7.95. If I go, whoa, why is it so big? If I go back up, it will show me that transaction. I could see all the numbers if I need to. I missed a 5 right there. 5 times 11.5. The reason I know that's wrong is I have 767 because I have the answer. Okay, and if I want to do this part, again, this is how we do it. We don't do this by hand and write down all. We do everything on a calculator. I could go back if I really want and just make each of those a square. Or I could just input the whole thing. It doesn't really matter. So 5.95. And to insert, okay. If I go second, insert a square. So I'm going to have to do that on each of those. Second, insert a square. Or I could just input it myself, you know, restart the thing. It doesn't matter, it's up to you. Second, insert a squared. Missed one. Insert a squared. oops, that didn't register, delete, insert a squared and a plus. And if I insert a squared and hit equal, and that should give me 6,235, 6,235.05. There. That's what I need for this. Notice what I got. I figured this part out. It's right there. And I figured this part out. It's right there. So if I get this formula, I need to multiply that by n divided by n into n minus 1. Well, n is 100. So if I take this formula and I fill in the blanks, I have s squared equaling n times the sum of f sub x squared minus the sum of f sub x squared over n into n minus 1. All what I did was copy that formula up there, and s squared will be, that's 100, sum of x squared, f times x squared, 6,235.05, minus the sum of f of x, quantity squared, 767 squared, all over n, which is 100. 100 minus 1 is 99. If I plug that in my calculator, I'm looking at, again, I'm going to use parentheses properly. So I would use parentheses 100 times 6,235.05 minus 767 squared, close parentheses, got it, divided by parentheses 100 times 99. I'll get 3.557. That's the variance. If they want to know what the standard deviation is, standard deviation would be the square root of 3.557. That would, and this is an approximation, right? Anytime you approximate, you put the dot or the squiggly line. If I take the square root of that, so take the square root, second square root of the answer, the last thing that I did, 1.89. So you always want to give one more decimal than the given. Alright. Rule of thumb. Data are significantly low if the value is 2 standard deviations below the mean. Data is not significant if the value is between 2 standard deviations. So this is the mean. You add a standard deviation and you subtract a standard deviation. You add another standard deviation and you subtract another standard deviation. This is considered okay, significant. If a number is right there, we call that significantly high. If a number is in that range, we call that significantly low. Remember, this is the average and this is the standard deviation. That's how we're going to set things are as we move along. Now, in general, the range is roughly 4 times the standard deviation. And that's why you're allowed to go 2 above and 2 below, which is 1, 2, 1, 2, 4 standard deviations altogether. So let's put that to test. Airport code. The data below are free download Wi-Fi speeds in megabits per second from 10 of the busiest international airports. Alright. So airport code. Denver, the Wi-Fi speed is 78.2. I don't know what that is. I guess that's Philadelphia. I'm not sure. 484. So they have all of these different airports and the speed at each one of those. If an international airport began to provide 60 megs per second free Wi-Fi and claim that their speed is miles above many others, would you agree? Well, if it's above, it should be 2 standard deviations above. So this is what you have to do. You need to figure out the average. The average of those measurements would be 78.2 plus 55.1, 48.4, 45.3, 43.7. I'm adding all of those. Plus 41.8, 32.2, 32, 27.7, and 22.9. Divide that by the standard deviation, which is a 10. The mean turns out to be 427.3 divided by 10. The average is 42.73 megabytes per second. That's the average. But this company is introducing 60. Well, I need to figure out the standard deviation. The standard deviation is going to be the square root of, there's 10 of those, times, now if I did this on my calculator, if I squared these values, and if I take the sum, which is 427.3, and I square that, divided by n times n minus 1, I'll get the standard deviation to be 15.98. So this is how we decide things scientifically. If you're asked any question, whether it's significant or not, what you would do, you would put the average on a number line. You would say, well, let's see how good that is. Put the average right there. The average is 42.73. Add 2 standard deviations and subtract 2 standard deviations. Any value that fall within that range is not that much different. It's like everybody else. Not that significant. So if I take my calculator, take 42.73, add 15.98 to it, I will get 58.71. If I add another 15.98 to it, I will get a 74.69. For anything to be considered significantly high, it must be above this number. Do you see that their value, 60, fall in there somewhere? So what's our conclusion? Our conclusion is that 60.8, it might seem to be really high, but it's not significantly high. To be considered significantly high compared to everything else, it should be more than 74.64. At least 2 standard deviations above, that would be significantly high. That's not the case. The last aspect of this lesson is one of the most crucial. Something that we're going to be playing with, a normal distribution. You'll learn all of these different names later on. For now, empirical rule. And this is what it states. Empirical rule says that a bell-shaped distribution has bell-shaped, another name for it, normal. Says that a normal distribution, a bell-shaped distribution, a symmetric distribution has, and this is what it is. You take the average. Within 1 standard deviation, if you add a standard deviation and you subtract a standard deviation, you're going to accumulate 68% of the measurements. If you take the average and you add 2 standard deviations and subtract 2 standard deviations, you're going to accumulate 95% of the population. And if you add 3 standard deviations and subtract 3 standard deviations, you're going to accumulate roughly 99.7% of the measurements. If you see the bell-shaped curve, symmetric, or a normal distribution, that's what it means. So look at this example really quick. It says the following data represent the age of all of 42, that's N, 42 female patients of a family doctor. We are told that the data has a bell-shaped curve. Awesome. And that the population mean is 57.2 years. And the population standard deviation is 12.3. What does that mean? Add 12.3 to 57, right? So this is the mean. The mean cuts the data exactly in half. If you add a standard deviation and subtract a standard deviation, you will get if you take 57.2 and add a 12.3, you will get 69.5. Add another standard deviation, 81.8. Add another standard deviation, 94.1. If you subtract the standard deviation, if you take 57.2 minus 12.3, 44.9. Subtract another standard deviation, 32 point, was that a 6? I didn't see it. 6, that's correct. And if you subtract another standard deviation, 20.3. So according to the empirical rule that we looked at, and this is the empirical rule right there, 68% of the measurements should be between those two numbers from there. 95 should be within those two, and 99.7%, almost all of them should be between those two values. Determine the percentage of all patients who are within 3 standard deviation. 99.7%. No need to even look at it. If it's a bell-shaped curve, those are guaranteed. Between what two values will this percentage lie? Well, between 20.3 years and 94.1 years. So basically you take the average and you add 3 standard deviations to get this upper. You take the average and you subtract 3 standard deviations. That gives you the lower. Now, again, it shows you how to do that in the calculator. I'm going to show you how to use the calculator to figure out everything that you need. But for this first exam material, we're going to use the calculator the way we just did. Same with the homework.